Introduction. Kamal and Deep are traveling in the train. Then, a train passes from the nearby track.
The train's whistle is so loud.
Yeah, it's really not tolerable.
I wanna ask you something.
Yes, Kamal, sure.
When the train passes us, the sound is loud, and when it moves away, the sound dies. Can you please explain me about this?
Okay, Kamal, I will tell you. This is due to the Doppler effect. The train producing sound waves was moving with respect to us. It causes an apparent shift in the frequency of sound waves for us. That's why sound rises when the train comes near us and dies when train goes away from us.
It's really interesting. I wanna know something more about this.
Students, today we will study about the wave optics. Objectives. At the end of this lesson, you will be able to define wavefront, know Huygens Principle, understand refraction and reflection of plane waves, describe plane wavefront in lens and prism, understand the Doppler effect, define electromagnetic waves, understand coherent and incoherent addition of waves, describe interference of light waves, explain Young's double slit experiment, explain conditions for sustained interference. Wavefront. Wavefront is defined as the locus of all the particles of a medium vibrating in the same phase at a given instant. A line perpendicular to a wavefront is called a ray. The phase difference between any 2 points situated on the same wavefront is zero. The shape of a wavefront depends upon the shape of the source of disturbance. The distance from one crest to the next crest is equal to wavelength lambda. The phase difference between any 2 points in the same phase on 2 consecutive wavefronts is 2 pi. So, at any given crest and trough, the phase is 2n pi and 2n plus 1 pi respectively, where n is an integer. Types of wavefronts. There are different types of wavefronts which are given as spherical wavefront. The wavefront of light waves radiated by a point source may be represented by spherical surfaces concentric with the source. Plane wavefront. At large distances from a point source, the spherical wavefronts are of very large radii and small portions of these can be considered planes. Cylindrical wavefront. A line source can produce a cylindrical wavefront coaxial with the source. Huygens Principle. Huygens Principle is a geometrical construction for finding the shape of a new wavefront at some instant. According to this principle, every point of a wavefront is a source of spherical secondary waves called wavelets, which spread out in all directions with the speed of propagation of the wave in that medium. The new wavefront at a later instant is the surface tangent to the secondary wavelets called the envelope of the secondary wavelets. Laws of reflection at a plane surface. The angle of incidence is the angle between the incident ray and the normal, but the ray is perpendicular to the wavefront and the normal perpendicular to the surface. Hence, the angle of incidence is the angle between the incident wavefront AB and the surface PQ. Similarly, the angle of reflection is the angle between the reflected wavefront CD and the surface PQ. Now, from the geometry of triangles BAC and DAC, AD is equal to BC and AD is equal to AC. We can say that these are congruent triangles. Hence, the angle of incidence is equal to the angle of reflection. Also, the incident ray, the reflected ray, and the normal are all in the same plane. Hence, the wave theory has proved the laws of reflection at a plane surface. Reflection of plane waves. Consider a parallel beam of light incident on a plane surface separating two media. The planes AB, A1B1 and A2B2 are the positions of the incident wavefront at different instants. A Huygens wavelet originating from point B in the wavefront AB will move a distance B' in the second medium in the same time that the wavelet from A expands in the first medium to include point A' on the surface XY. Since the two wavelets have radii A' and B' are not in the same medium, they move with different speeds, say V1 and V2 respectively. Case 1. If medium 2 is optically denser than medium 1, then V1 is greater than V2 and hence A' is greater than B'. The ray is bent towards the normal. Case 2. If medium 2 is optically rarer than medium 1, then V1 is less than V2 and hence A' is less than B'. The ray is bent away from the normal. Distance A' is equal to V1 is equal to lambda 1, the wavelength of light wave in medium 1. Distance B' is equal to V2 is equal to lambda 2, the wavelength of light wave in medium 2. Therefore, V1 by V2 is equal to lambda 1 by lambda 2, or it can be written as V1 by lambda 1 is equal to V2 by lambda 2 is equal to nu. The above expression shows that the frequency of the light wave remains unchanged during refraction. The wavelength decreases when the light wave refracts into a denser medium and the wavelength increases when the light wave refracts into a denser medium. Plane wavefront in lens. Consider a plane wavefront ACB incident on a double convex lens. According to Huygens' hypothesis, each point of the wavefront acts as a source of secondary waves. These secondary waves will travel through different thickness of the lens. The time taken by the secondary wave to travel through CP1 in air plus P1 P2 in lens will be the same as the time taken by waves to travel through AX plus XD in air. So, all the secondary waves from the incident plane wavefront ACB reach dP2E at the same time. Thus, dP2E is the refracted wavefront. This wavefront is converging in nature. Plane wavefront in prism. Consider a plane wavefront BD incident on the prism. According to Huygens' hypothesis, each point of the wavefront acts as a source of secondary waves. These secondary waves will travel through different thicknesses of the prism. The time taken by a secondary wave to travel through distance BC in the material of the prism is the same as the time taken by a secondary wave to travel through a distance dA plus AE in air. The distance travelled in air is clearly greater than the distance travelled in prism. This is because the velocity of secondary wave in the material of the prism is less than that in air. All the secondary waves starting from BD reach CE at the same time. So, CE is the emergent wavefront. The Doppler effect. Consider when there is a medium and the source moves away from the observer, then latter wavefronts have to travel a greater distance to reach the observer. The time taken between the arrivals of two successive wavefronts is hence longer at the observer than is at the source. Thus, the frequency as measured by the source will be smaller. This is known as the Doppler effect. The Doppler effect is observed whenever the source of waves is moving with respect to an observer. The Doppler effect can be described as the effect produced by a moving source of waves in which there is an apparent shift in frequency for observer. Redshift and blue shift. Redshift. The increase in wavelength due to Doppler effect is known as redshift because the wavelength in the middle of the visible region of the spectrum moves towards the red end of the spectrum. Blue shift. When waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. The Doppler shift is given by delta nu by nu is equal to minus v radial by c, where v radial is the component of the velocity along the line joining the source and observer. Electromagnetic waves. A wave of energy consisting of electric and magnetic fields is known as electromagnetic wave. Variations in both electric and magnetic fields occur simultaneously. As a result, they attain their maxima and minima at the same place at the same time. The directions of electric and magnetic fields are mutually perpendicular as well as to the direction of propagation of the wave. Thus, these waves are transverse in nature. The velocity of the waves depends entirely on the electric and magnetic properties of the medium in which these waves travel. Superposition of waves. Principle of superposition states that when two or more than two waves travel in the same medium at the same time superimposing each other, then the displacement of the resultant wave at any instant is equal to the vector sum of the individual displacements at that instant. Let vector y1, y2, y3 and so on be the displacement vectors due to the individual waves at any instant acting separately, then, according to the principle of superposition, the displacement of the resultant wave at that instant is given by vector y1 plus y2 plus y3 plus so on. Coherent and incoherent sources of waves. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency, and in same phase or having constant phase difference. There are two general methods for producing coherent sources are follows. By division of wavefront. In this method, the wavefront is divided into two or more parts by use of mirrors, lenses, or prisms. By division of amplitude. In this method, the amplitude of incoming beam is divided into two or more parts by partial reflection or refraction. These divided parts travel different paths and are finally brought together to produce interference. Incoherent sources emit light with frequent and random changes of phase between the photons. Tungsten filament lamps and ordinary fluorescent tubes emit incoherent light. Interference of light waves. Interference of light is the phenomena of redistribution of light energy in the medium due to superimposition of light waves coming from two coherent sources. There are two types of interferences. They are constructive interference, destructive interference. The interference is constructive at the points where the resultant intensity of light is maximum, and the interference is destructive at the points where the resultant intensity of light is minimum. Constructive and destructive interference. Constructive interference. At the points of the medium where the resultant intensity of light is maximum, the interference is called as constructive interference. For constructive interference, phi is equal to 2n pi or p is equal to n lambda, where n is equal to 0, 1, 2, 3 and so on. Phi is equal to phase difference. P is equal to path difference. Lambda is equal to wavelength of light. Destructive interference. At the points of the medium where the resultant intensity of light is minimum, the interference is called as destructive interference. For destructive interference, phi is equal to 2n plus 1 pi or p is equal to 2n plus 1 lambda by 2. Young's double slit experiment. In Young's experiment, monochromatic light from a source passes through a narrow slit S and falls on two closely spaced narrow slits S1 and S2 placed at some distance from S. The slits S1 and S2 act as coherent sources of light waves because the light from each is derived from the same primary source S. These waves interfere constructively and destructively at different points on the screen to produce a pattern of alternating bright and dark bands called interference fringes on the screen. Mathematical analysis in Young's double slit experiment. Let S1 and S2 be coherent sources at separation d and capital D be the distance of screen from sources, then path difference between waves reaching at P is given by product of yn and d divided by capital D. For maxima delta is equal to n lambda, position of nth maxima is given by n capital D lambda upon small d. Position of nth minima is given by n minus 1 upon 2 into capital D lambda upon small d. Fringe width. Fringe width is defined as the separation between two consecutive maxima or minima. Beta is equal to y into n plus 1 minus yn, which is equal to capital D lambda upon small d. Angular fringe width is given by beta upon d, which is equal to lambda upon d. Use of white light. When white light is used to illuminate the slit, we obtain an interference pattern consisting of a central white fringe having on both sides symmetrically a few colored fringes and then uniform illumination. Example. Let's take an example on Young's double slit experiment. The two slits in Young's experiment are 3 mm apart, illuminated by a light of wavelength 480 nanometer. The screen is at 2 meters from the plane of the slit. Find the separation between 8th bright and 3rd dark fringe with respect to central bright fringe. Let's see the solution. Distance of 8th bright fringe from center is given by 8 capital D lambda upon small d. Distance of 3rd bright fringe from center is given by 5 capital D lambda upon 2 small d. We have y is equal to y8 minus y3. By putting the values and calculating, we get y is equal to 11 capital D lambda upon small d. Putting the values in the above equation and calculating, we get value of y is equal to 3.52 millimeter. Hence, the separation between 8th bright and 3rd dark fringe with respect to central bright fringe is 3.52 millimeter. Conditions for sustained interference. The following conditions are necessary to obtain a continuous or permanent interference. The light should be monochromatic. If this is not so, the fringes of different colors will overlap. The two sources producing interference must be coherent. The wave trains causing the interference must have light waves of the same wavelength and same velocity. The two interfering wave trains must have the same plane of polarization. To observe interference fringes clearly, it is necessary that the fringe width is sufficiently large. Did you know? For manufacturing reasons, a perfect lens has a spherical surface shape, though theoretically the ideal surface should be aspherical. Light slows down, bends towards the normal, and has a shorter wavelength when it enters a higher refractive index or as it moves to denser medium. Reflection of waves of sea walls or other barriers can cause an interference pattern called a standing wave. In standing waves, crests do not move laterally. Summary. Let us summarize what we have learned. Wavefront is defined as the locus of all the particles of a medium vibrating in the same phase at a given instant. Every point of a wavefront is a source of spherical secondary waves called wavelets. The wavelength decreases when the light wave refracts into a denser medium. The Doppler effect is defined as the effect produced by a moving source of waves in which there is an apparent shift in frequency for observer. When waves are received from a source moving towards the observer, there is an apparent decrease in wavelength. This is referred to as blue shift. A wave of energy consisting of electric and magnetic fields is known as electromagnetic wave. Coherent sources of light are those sources of light which emit light waves of same wavelength, same frequency, and in same phase or having constant phase difference. Interference of light is the phenomena of redistribution of light energy in the medium due to superposition of light waves coming from two coherent sources.